Alright, hello everybody, and today we're going to be integrating the natural log to the kth power of x, where k is some natural number. So if you don't know what this notation means, that's just the same as natural log of x raised to the kth power. I'm using this notation because it's a little bit cleaner. So yeah, let's just jump straight into it, I guess. So I already defined this integral as I sub k here, where this k right here, this subscript, will represent the power on this natural log here. So this will be important later on because we're going to use recursive formulas to solve this integral. So let's take a look at this function first of all. I hope you agree with me that nothing would change if we simply multiply this thing by 1. Well, because now we have something we can differentiate and something we can integrate, and whenever you can do that, well, maybe it's a good idea to use integration by parts. So I'm going to do the DI method here, so just draw up a little table here. So we want something to differentiate. That's obviously going to be natural log to the kth power of x, and we're integrating this 1 here. So differentiating that, we get k times natural log to the k minus 1 power of x, and remember the chain rule, we have to multiply by the derivative of the inside, which is just this natural log of x in this case. So that just becomes 1 over x, so I'm just going to write it like that. And integrating 1, we just get x. So the result of this integral will just be the product of the diagonals here, and this row here will be a new integral. So what we end up with is x times natural log to the kth power of x, and then we have minus here, and then now we have another integral. But notice that this x and this x will cancel, and we have this k, that's a constant, we can bring that to the outside, and we have natural log to the k minus 1 power of x dx. Alright, and let's take a look at this integral here. That kind of looks similar to what we have here, because this subscript here represented the power up here. So this thing is actually I sub k minus 1. So we can rewrite this a little bit. So our I sub k turns into x times natural log to the kth power of x minus I sub k minus 1. And notice something important here. This subscript here, this k, appears here, here, and here it turns into k minus 1. So how about let's find an expression for this I sub k minus 1. Well, I sub k minus 1 will be equal to x natural log, and now instead of the kth power here we have the k minus 1 power of x minus k minus 1 I, and this k here will reduce by 1, so we have k minus 1 is nothing but k minus 2. Let's do one more iteration, so let's try and find an expression for I sub k minus 2, or that's just x natural log to the k minus 2 power of x minus k minus 2 I sub k minus 3. And we can actually keep going with this process k times, and we'll actually end up with I sub 1, because remember, k is a natural number, so we will be destined to land on 1, which is also a natural number. So if we keep going with this process, we have I sub 1 being equal to x natural log, and this turns into a 1, so let's just leave it out. So natural log of x minus, and this turns into a 1, and then we have I sub 0. But notice if you plug 0 into this k here, well, we're going to have natural log to the 0th power, which is just 1, and you're integrating a 1, so that's just going to leave you with an x. So this I sub 0 here just turns into an x. So this will be the final line of our recursive formula here. So maybe let's combine all of this stuff together and see if we can find some kind of pattern we can work off with. So let's start by substituting this whole line here, so this line, for I sub k minus 1, because this is equal to I sub k minus 1. So if we do that, we're going to end up with, I'm just going to rub it out here. Alright, so I substitute this part into here, and now let's do the same for I sub k minus 2. And notice that I sub k minus 2 is exactly this line here. So we're going to just dump that into here. Alright, so after substituting all that into here, let's expand out all the brackets and we should be able to find some kind of pattern that appears. So I'm going to just do that quickly. So this is equal to... Alright, so I've expanded out all these brackets here and I've just put down a dot 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 because this pattern will just keep going until it reaches 1. And here comes the fun part of the video in my opinion, because now you have to express all these k number of terms or whatever it is in terms of a sum. Alright, so let's have a look here. First observation, these signs here alternate. So you have minus, plus, minus, and this is a plus right here. And also notice that we have this coefficient in front of the first term is 1. So we have 1, and then we have a k, and then we have a k minus 1, and then we have a k minus 1, and a k minus 2, and the next one will be k minus 1, k minus 2, k minus 3. So it's kind of like a factorial that keeps getting truncated when you move this way. So what do I mean by that? Well, you see this one here is nothing but k factorial over k factorial. And this k right here is the same as k factorial over k minus 1 factorial. And you can check this for yourself if you just think about it like 5 factorial over 4 factorial, where you have 5 times 4 times 3 times 2 times 1 over 4 factorial, which is 4 times 3 times 2 times 1. All of this stuff will be cancelled out and you're just left with this 5 here. So that's kind of like what's going on in this case right here. And for this term we have k factorial over k minus 2 factorial. And for this part here we have k factorial over k minus 3 factorial. So how about let's write all of this stuff in terms of these k factorials here. Alright, so I've expressed all of these coefficients in terms of k factorials. So now we can really see some kind of pattern emerging, because all these k factorials are kept constant throughout every single term, and in the denominator here it changes by 1 step every term, you could say. So now let's consider what would happen to this series of terms as it goes towards 1. So remember what I wrote about the I sub 1 case. So if you have I sub 1, that's nothing but x natural log x minus x. This will kind of be like the last term inside of our final answer. So what we can do is say that this series keeps going, so I'll just continue it here. So dot dot dot. So we'll have an x, natural log of x, and then an x term hanging off the ends here. And the problem is we have to figure out what the coefficients are and whether it's a plus or a minus. So let's how about work out these coefficients first. So at the start of the chain we have k factorial over k factorial. As we keep going, these denominators inside these factorials here will keep decreasing by 1. Well, if we do it k amount of times, well, the coefficient in front here will be k factorial over 1 factorial. So this denominator here, the factorial will keep decreasing all the way to 1. And for this last term here, it will be k factorial over 0 factorial. Another way to confirm this is to look at this exponent of the log here. So you have a k matching with k factorial, k minus 1 matching with k minus 1 factorial, and sure enough, you have natural log to the first power here matching with 1 factorial right here. And here it's kind of like natural log to the 0th power of x, which is just 1, matching with the 0 factorial. So now you have to find out whether it's a plus or minus for these last two terms here. Well, notice that the first term is always positive. So since we have an alternating series of pluses and minus, obviously we would have a minus 1 to the something, and then plus a minus 1 to the something here. So let's analyze some things here. So let's take the case where k is an even number. So if we have k being an even number, well, so we have this term that's positive, and every single second term is positive. So this will be positive, this will be positive, The next one, k minus 4, will be positive. And remember that k is an even number. So what you can deduce from that is that every single even power of k will have a positive coefficient. And this one here, 1 is an odd number. So we want the coefficient of this term here to be a negative because it's odd. So how can we get a negative from this -1? Well, we just have k, but remember k is an even number. And whenever you have -1 raised to the even number, we just get 1 or a positive. So what you have to do is add a minus or +1 here. And for this last term here, 0 is an even number. So what you can just do is put a k here, because k is an even number, and this will turn positive. So we'll just put a positive in front here as well, because this will be negative anyways. Alright, so what have we established here? We found out how to figure out the coefficients, including the sign, whether it's a plus or minus of each term. So now let's bring everything together. So I'm going to rub out this line right here. So let's kind of bring this all together. What I'm going to do is I'm going to write the last term first, because if you haven't figured out already, we can actually express all this stuff in terms of a sum. So because we have a 0, it would be nice if we start with the last term first. So we have an index running from 0 to, I guess, k. So our first term will be this one, and that's -1 to the kth power. And what we can also add to this power is -0, and you'll see why in a sec while I'm doing this. So I'm going to highlight this 0 in blue, just to make it clear later on. And we have this k factorial over 0 factorial here, so I'll just write that down, k factorial over, and I'll write it down here, 0 factorial. Alright, and we have an x right here. And there's no natural log here, but we can actually write a natural log to the 0th power of x here, just to keep everything consistent, because we have natural logs in every single one of these terms, so we might as well put a natural log to the 0th power. This part's just 1, just to be clear. So we have natural log to the 0th power of x. Alright, so next term we're going to add. So we're going to start off with this -1 thing here first. So we have -1, and here it's k minus 1. So I'll highlight this -1 in blue. So k minus 1. And then we have k factorial over 1 factorial. And here we have x natural log to the first power of x. Alright, so this will keep going. So you have plus ... So finally we arrive near the end here, where we get to this first term here. Alright, so I've rewritten everything that we had so far, again in this form right here. And notice that I've replaced all the plus minus alternating thing with -1 to its respective power. So you can check here that this last term here, which was the first term before, is positive, because k minus k here is 0, and -1 to the 0 is positive. So I really hope that you see the pattern here, because everything that I've written in blue is everything that changes as each term progresses. So now what we can actually do is express all of this stuff here in terms of a sum. So let's just write down the sum first, and let's just pick some new index, I don't know, j. And j will represent everything that's in blue here. So the first term here is 0, and it ends on k, so j goes from 0 to k. And let's write down this -1 thing first. So we have -1, and notice we have k minus something, so that's k minus j. And we have k factorial next, so k factorial, and this blue here, that's this j factorial, and then we have x natural log, and then this power here is also j, because it's in blue, of x, and yeah, that's pretty much it. So this expression here that we've written as a sum is in fact I sub k, as we wanted to find at the very start. So this whole thing here is I sub k, which was the integral that we wanted to find. But we're missing one little thing, and that's just a plus c at the end. So this is the answer to our integral, natural log to the kth power of x. And I'm just going to put in something a little bit extra here. So if you want to evaluate this integral with upper and lower bounds, since this is the antiderivative, you just need to plug in the upper and lower bounds, I guess. So if you have the integral from a to b, natural log to the kth power of x dx, well, first of all, you have your primitive here, which is the sum from j equals 0 to k of all of this junk inside here. And you want to evaluate all of this stuff from a to b. And notice that's just replacing all the x's with b's and then a's. And if you do that, what you should end up with is the x's turning into b. So you have b ln to the jth power of b. But since this part is the only part that's dependent on x, you have to subtract the lower bound, which is a natural log to the jth power of a. You can do it the long way and expand out all of the sum, and then you can factor it, and this should be the result that you end up with. And just because, since you have natural log of something here, your upper and lower bounds have to be greater than 0. And this should be a j factorial here. But yeah, that's pretty much it. Hope you guys enjoyed this video, and I'll see you guys next time.